All right, we're going to continue finding the volume of solid bodies. Here we're going to look at the volume of a sphere. Some of you may already know the fact that the volume of a sphere of radius r is 4/3 pi r cubed, and we're going to derive that now. Remember where our definition of volume is. We're going to talk about finding this cross-sectional area at a height of y, right? We slice through the solid body at a height of y, and we get this area, and we're going to integrate that area function to get the volume. So of course a sphere is a big ball, right? Here's an example of what a sphere would look like on a two-dimensional sheet of paper with the hidden line there, and right in the center of the circle, right from the center to some point on the edge, that's our radius r. And so what I'm going to do is I'm actually going to slice this. Got a little bug flying on my paper. That was interesting. I'm going to look at the top half of the sphere here. And so what I'm going to do is put it so that the top half of the sphere sits on the x-axis. So I'm going to just look at the top half. I'm going to find the top half of the sphere. I'm going to find the volume of that, and then just double it to get the volume of the sphere. Okay. So we have here. This is the x-axis. This is y equals 0, and then what's the height here? Well, remember this radius, right, from the very center of our circle. If I go from the center of the circle, the sphere, to the point right on the sphere itself, right, that's distance is the radius, right? So that means this must be y equals r here. Okay, so the height at that point is r. So what we're going to do then is we're going to come up some arbitrary height here, and we'll call that height y, and I come across and slice right across there, and cut that slice out. Now when I take that slice out, what's it going to look like? I slice that, pull it out, and flip it over. It's going to be a circle, right? And so the circle, what's the radius of the circle going to be? Well, as y gets bigger and bigger, the circles get smaller and smaller, right? And the radius of that circle, let's say from this point, the center of the circle, out to the end, let's call that I don't know, a. Okay, so that length is a, and a varies, right, from here down here. The value of a would be equal to r, right, from the center of the sphere to the end is r. But as we move up, that value of a is getting closer and closer to 0 as y goes from 0 to r. Okay, and so the area as a function of y again is what the area of a circle, pi times the radius squared. So I need to figure out a way to relate a to the variable y, and this is how I'm going to do that. I will first of all note that this height, right, is the same as y here, so that's y. Okay, and then here's what I'm going to do. This is the center of the sphere. This is a point on the sphere. If I draw this line segment from the center to that point, how far is this? That's the radius r, and this is a right angle. And what do we have here? We have a right triangle, right? So by the Pythagorean theorem, I can relate the variables a to y. Remember, r is a fixed quantity, right? It's the radius of our sphere, so it's fixed. So this is the hypotenuse of this right triangle. Do you see that right triangle? And so this side length is a, which is the radius of our little sliced piece. Y, right, is the height up from the from the x-axis rather that we are, and then r is that fixed hypotenuse. So I know that a squared plus y squared is equal to r squared by the Pythagorean theorem. Now I need to know what a squared is. I can solve for a squared by just subtracting y squared. And so from that, I see that my area as a function of y is pi times a squared, which is r squared minus y squared. And there is my cross-sectional area. Now what do we want to do? We want to integrate that cross-sectional area, and I'm going to integrate it from y equals 0 up to y equals r. Remember, when I do that, I'm going to get the area, the volume of what? The top of this sphere, the top of this sphere. So I want to know the total volume of the sphere, so I'm going to double it, right? So I'm going to make sure I do what? 2 times the integral from 0, y equals 0 to y equal r. Remember, r is a fixed value. And a of y here is pi r squared minus y squared dy. And there's our integral. So remember, r is a constant in this. This pi can come out, so there's 2 pi. And what's the antiderivative of r squared with respect to y? Remember, r is a constant. So say r was equal to, say the sphere's radius was 10. 10 squared would be 100. What's the antiderivative of 100 with respect to y? It's 100y, right? So it's whatever r squared is, y. And then what's the antiderivative of y squared? That is a variable now, right? That's 1/3 y cubed. And we're evaluating y, right? Y equal r to y equals 0. We're going to subtract. So I replace y here. Pull this 2 pi out. I replace y, first of all, with r. And so what do I get? R squared times y is r. R squared times r is r cubed. Minus 1/3 y is r cubed. There's where I'm plugging in at y equal r. Minus y equals 0, but if I plug in 0, this is 0 and this is 0, so I get 0. And this is r cubed minus 1/3 r cubed. 1 minus 1/3 is what? 2/3 r cubed. 2 pi times 2 is 4 pi over 3 r cubed. And if you go back up, I've got 4/3 pi r cubed. That's the same thing as this. And so indeed I have verified and proven the volume of a sphere of radius r is 4/3 pi r cubed. Okay. I want to do one more. And let me talk a little bit about this next one here. So the same setup again. We're going to set up the integral needed to find the volume of the solid which has a circular base of radius 2 whose parallel cross sections perpendicular to the base are squares. Okay, so let's see what this is going to look like. This time I'm going to set this up a little bit differently. I'm going to draw in the XY plane here the base. And so instead of having this object like I've been having it, going up from the bottom to the top up the paper, I'm going to let the bottom be the paper itself, and the top is coming towards you, towards the camera here. Okay. If I look at, say, a radius of 2 going in either direction, this would be -2, of course, down to -2 to +2, I can draw this circle. So drawing this circle here. Okay, radius 2. So there's my circle of radius 2. All right, all the way around. And then what we have is I'm going to integrate with respect to x this time. And what I'm going to do is I'm going to come out here an arbitrary distance x here. Okay, and let's say right here, so that this distance here is x. Okay, come out some arbitrary x value here, and this is the object is coming towards you. And so when I slice, I'm going to slice this way, and there's a slice. So the slice is perpendicular to the square base are squares. So if I pull this slice out, if I lift it out, pull it out, and lay it flat, what should I see? I should see a square. Okay, should see a square. Okay, and the area of this square is now area as a function of x. I'm going to integrate with respect to x-axis here, right? So as x varies, I need a formula for this. If I let's let the height here be a, okay, from the x-axis up to this point on the circle. Let this be a. So notice that this also is a here by symmetry, and so our side length here, what's our side length here? It's 2a. Do you see that? The way I've got set up, if this is a, then this is also a, so this is 2a. And I can find now the area of a square. It's square, so all the sides are 2a, and so the area of the square is 2a quantity squared, which is 4a squared. Okay. So the question is, can I relate a now as a function of x? Can I relate a and x? Well, again, I hope you see it. We have this right triangle right here. This is x, this is a, and this is 2. And so again, by the Pythagorean theorem, what do we have? We have x squared plus a squared is equal to 2 squared. 2 squared being 4. And notice then I get that a squared is 4 minus x squared. And so with this information, I'm able to deduce now that the area of the function of x is 4 times a squared, which is 4 minus x squared. Or if I want to distribute that 4, the area is 16 minus 4x squared. That's the cross-sectional area of these squares. And notice that makes sense. If x is 0, right, if I slice right here, then I've got a square coming up here. And what's the side length of the square? From -2 to +2. It's 4, right? And the area of a square of side length 4 is 4 times 4, 16. 4 squared, 16 units, right? Square units. That's the area of that. Is that true when x is 0 in our formula? If x is 0, what do I get? 16. Yeah. And notice as we move downward, right, those squares' side lengths are getting closer and closer to 0. In fact, when x is equal to 2, we should get 0. Is that true? 2 squared is 4. 4 times 4 is 16. 16 minus 16 is 0. And let's now find the volume of this solid. We're going to do this. We're going to integrate from -2 all the way to +2. Okay. There is some symmetry here. I could use a similar argument to what I did with the sphere, but I'm going to find the volume by going from -2 to +2. And the area is 16 minus 4x squared. It's a pretty easy function to integrate. There's the setup. This was just set up the integral here. So this is the answer. If you want to check it out, I'll let you finish that out. You can do that and show that it's 128 thirds. I'll let you do that. That's the cubic units, right, for this solid. Now, some of you might be wondering, what does this solid look like? Well, my daughter has actually 3D printed me this object, and I'm going to show it to you right now. If I set it down in this configuration, it would look like this. So that's what it looks like looking at it from the top. Let's look at it from the side now. So if I'm looking at it this way, let's see what it looks like. Do you see the square shape? Right? That's what we're talking about, the square shape. And this square that we're looking at, the big square here we're looking at, is the square you get. That's the biggest square. If you notice the sides, when you look at the sides, right, these if I cut down, see that little line right there, if I cut down and pull and slice through that and pull that out, I'll have a square as well. But notice the squares are getting smaller as we move closer, right? As x gets bigger and bigger, these square side lengths are getting smaller and smaller and smaller. And you can see that as we move around, the side lengths, the square side lengths are getting smaller and smaller as we move across here. And the squares, they're if I slice all the way through like that, all the way down, I'll have a square. But the side lengths are getting smaller and smaller. So there's the object. It's really kind of cool. She 3D printed that to me. Some of you know how to do that kind of stuff, and so it's quite amazing. But this is what this object looks like, and we found the volume of it. And so there we go. We're going to stop with volume now. There's plenty of practice for you in the homework, and it is a challenge, I think, but it's something that you'll need to work on and practice, because there's things like Pythagorean Theorem being used, there's things like similar triangles being used, and setting up, that's the hard part. Usually the integration is pretty easy when you get there. Okay, we'll stop the video for now. The next video, actually in this area, we're going to take a look at not volume, but it's related in a sense. It's an application, if you will. We're going to look at the average value of a function, and we're going to define that in terms of an integral and play around with that a little bit in the next video.